National Academy of Mobile Electronics is proud to present a series of training videos for the consumer electronics industry. Each video focuses on a specific area of training with information that has been compiled and painstakingly applied over several years. These videos will make a great addition to your video training library, and if you're just getting started, they will save you hundreds of hours of head scratching. So sit back, take notes, and enjoy. Here's Mike Breault.
Hello, my name is Mike Breault, and welcome to the National Academy of Mobile Electronics. NAME has developed a series of highly comprehensive training videos for the mobile electronics industry. Our videos will help the seasoned professional as well as the novice installer to better enhance their installation skills. We hope you enjoy our videos, and if you have any questions regarding any of our other training programs, please feel free to call our toll-free number during business hours. Now, let's get to work. I've been in the mobile electronics industry for over 16 years, serving in several different capacities. One thing I can say about this industry is you can never know too much. A day wouldn't go by when I didn't learn a new trick about installing or a new technique to implement. Our goal here at NAME is to help you reduce the amount of time you spend on an installation by helping you eliminate the time spent on trial and error. This will make you worth more money to both yourself and to your employer. We're confident that the techniques revealed in these videos will prove effective in your quest to build a better career as a mobile electronics specialist.
Loudspeakers. Without them, our job would be non-existent. They are the final stages and the tell-all of how well a system is designed and installed. In this video, we will be covering several aspects of low-frequency loudspeakers and how to design and build various types of enclosures to reproduce good quality, crisp, clean, low frequencies for your automotive audio system. We will talk about the makeup of a transducer, the derivation of teal small parameters, several formulas for designing enclosures and calculating the proper size of these enclosures. We believe that any loudspeaker has the ability to reproduce good sound given the proper type and size enclosure. Before we go on, let's look at what we will be covering. In Part 1, we will be covering a couple of important theories dealing with basic acoustics, the makeup of a moving coil dynamic loudspeaker, characteristics of the transducer, and we will also be defining teal small parameters. In Part 2, we will be covering basic geometry, the golden ratio, and figuring displacement of both your speakers and ports. In Part 3, we will go over the derivation of teal small parameters for your loudspeakers, formulating acoustic suspension enclosures, formulating bass reflex enclosures, which includes port length and size, and finally, in Part 4, we will cover formulation of isobaric enclosures and the formula for bandpass enclosures. Now, let's begin. Before we can talk about the loudspeaker and the enclosures to house them, we must first learn a bit about basic acoustics. What exactly is sound? Sound occurs at the moment any body with a greater mass than the body surrounding it is set into repeated motion. Sound wave propagation is the alternate compression and decompression of air immediately surrounding an object, and then the air around the object compresses itself. These sound waves propagate outward in a spherical motion until the sound initially produced is dissipated or absorbed into the air. If we were to graph the radiating waves propagating from a loudspeaker, it would occur in cycles of high and low levels of energy. Here is how a 20 Hz sound wave might look if we were graphing it. Let's compare that to a 100 Hz tone. Before we go on, let me explain what exactly we mean by Hertz. Hertz is a unit of measurement for the frequency in which a full wave will occur in exactly 1 second. For instance, 20 Hertz is equal to 20 cycles per second, or a sound wave will propagate from 0 degrees to 180 degrees and on to its original starting point, or 360 degrees, 20 times in 1 second. Much like a speaker must complete 100 cycles per second to reproduce a 100 Hz tone. This gives you a slight idea of just how incredible a loudspeaker really is. When it is asked to reproduce frequencies of 30 Hz to 1000 Hz simultaneously, and it does it virtually while turning on a dime. Now that we have discussed cycles per second and full waves, it is important to note the significance of the quarter wave. Here is the dissection of the full wave. The human ear is able to detect sound in as small as a quarter wavelength. We'll show you the importance of this a little later. How does the speed of sound affect what we hear? We will cover this briefly. Sound travels at approximately 1132 feet per second. Well, since we know that sound is measured in cycles per second, then it is possible for us to conclude the wavelength of any sound wave. Simply by dividing the speed of sound in feet per second by the frequency, we will arrive at that wavelength. For example, the wavelength of a 200 Hz tone would be 1132 divided by 200, or 5.66 feet. Now divide this by 4 to find the quarter wavelength of this frequency. As you can see here, the reason for low frequencies being non-directional is all physical. The width of the distance between the human ears is about 9 inches, and when calculating that, you come up with the quarter wave being about 377 Hz. Therefore, anything under 377 Hz we will not perceive in stereo. What other interesting questions may arise from our findings? Let's look at the cab of this pickup truck. Its width is about 6 feet wide, which is the greatest distance in the cab as compared to front to back measurements. Now, multiply 6 feet by 4 for the quarter wave and divide by 1132. You will find the lowest quarter wave to fit into the cab of this vehicle is about 47 Hz. Now you can see how low frequencies are affected in large and small areas. Now we will briefly cover sound measurements in regards to its loudness. Sound pressure level, or SPL, is the loudness of sound in decibels in which sound is measured. The decibel is a logarithmic unit of measurement equal to 1/10 of a bell. It was named by Alexander Graham Bell and is the smallest division in which the perception of change can be noticed by the human ear. Now, let us see how power and distances affect sound. For the human ear to perceive a sound as being twice as loud, that sound must increase by approximately 10 dB, or decibels. Well, in order to increase our sound by only 3 dB maximum, we must double our power to the system. So, in other words, an increase from 10 watts to 20 watts improves sound by 3 dB. Just as adding to a system of 200 watts an additional 200 watts will improve your volume, or SPL, by 3 dB maximum. This also means to make a system twice as loud, you must increase your power by about 8 times. Just as power will affect the SPL of your system, we get a different effect by moving a loudspeaker closer or farther away from you. We will notice 6 dB changes in the halving or doubling of distances. For instance, if a speaker is 2 feet away in your door and its volume is at 90 dB, and the same type of speaker is 4 feet away, the speaker that is 4 feet away will be a full 6 dB down, or at 84 decibels. This may help when you are looking at the sensitivity specifications of a loudspeaker given out by a manufacturer. If one manufacturer lists his speaker as having a sensitivity of 96 dB at 1 watt at 1 meter, and another manufacturer lists his speaker at 99 dB at 1 watt at half a meter, which one would you say is more sensitive? Right, the first one. The second, using the same parameters, would measure 93 dB at 1 watt at 1 meter. Now, let's continue with the moving coil dynamic loudspeaker. Here is a basic diagram of a moving coil loudspeaker. Its parts makeup is as follows. The chassis, or basket, is generally made up of a pressed steel, and it provides the housing for all of the other components. The magnet assembly, which provides the magnetic field through the voice coil, as the current in the voice coil changes, it uses the polarized force of this assembly to travel through. The voice coil is a hollow tube wound with generally thin copper wire and is attached to the diaphragm or cone. The cone may be made up of a variety of materials, but for the most part you will see them made mostly of a rigid paper material. The cone is the component which radiates sound. The spider's primary function is to center the voice coil in the magnetic gap. It also does add some stiffness to the speaker's suspension. The surround joins the cone to the basket and offers flexibility for which the cone to move. The stiffer the material, the higher the QTS of the speaker will be. The lead wires are made up of a flexible wire which attaches the voice coil to the chassis. Alright, now let's cover some basic characteristics of the loudspeaker. Let's talk a bit about the piston range of a loudspeaker. The piston range is defined as the range of frequencies in which the acoustic wavelength is greater than the diameter of the diaphragm. Sound waves with frequencies above the speaker's piston range are radiated from the surface of the cone instead of from the piston-like motion. This response gives the cone material somewhat of an internal dampening characteristic. Thus, the polar response narrows, which causes the off-axis response to attenuate with increasing frequencies. Now, let us cover a definition of teal small parameters in which will make our enclosure building ventures a much more enjoyable experience. The teal small parameters which we will be most concerned with are going to be the Fs, which is the frequency in which the loudspeaker resonates in free air and is where the speaker operates most efficiently. Next, we have the QTS. This is a measure of the speaker suspension. The stiffer the suspension, the higher the QTS will be. Finally, we have the VAS. This specifies the airspace in a sealed enclosure which would match the compliance of the speaker. Once derived, these parameters will make it possible to predict the response of your enclosures. We will cover more on teal small parameters in Part 3, but for now, let's move on to Part 2. We will begin with basic geometry. First, we will talk about figuring basic formulas for finding the area of a particular shape. As you can see, for a rectangle, you simply multiply the length times the width. For a triangle, it is half the length times the width. And for a circle, it is pi r squared, or 3.14 times radius times radius. Now, in figuring the volume of a particular shape, it is as follows. For a rectangular box, simply multiply length times width times depth. For a triangular shape, it would be half the length times width times the depth. And finally, for a cylindrical shape, pi r squared times the length. Now, let's look at the calculation of some odd shapes you may encounter and see how to derive their volumes. Here is a basic shape of a mini truck box. Let's see how to derive at a volume for this shape. Our top is 3 inches. Our bottom is 6 inches. Our back is 12 inches, and it is 18 inches wide. For this, simply add the top and the bottom, which is 9, divide by 2 to get 4.5, and now multiply by height and width, or 4.5 times 12 times 18 to get 972 cubic inches. One important thing to note is that these are inside dimensions. So if you have taken outside dimensions and have used 3/4 inch MDF, reduce your measurements by 1.5 inches. Now, let's see how to convert the 972 cubic inches into cubic feet, since cubic feet and liters is what speaker VAS is generally given in. To do that, take your total volume of inside airspace and divide it by 1728, which is how many cubic inches it takes to make up a cubic foot. In our case, our enclosure was 972 cubic inches. So 972 divided by 1728 is 0.562 cubic feet, or just over half a cubic foot. To convert that to liters, you need to know that there are 28.317 liters in 1 cubic foot. So simply multiply by 0.562 and you'll see your enclosure is 15.914 liters before figuring displacement. Now, let's see how to derive a tough dimension on a triangular shape. Here you are designing a box for the rear of a pickup, and you know that the depth on the bottom is 6 inches, the top is 3 inches, the back is 12 inches. But you can't figure the front until you have cut and assembled your other sections. Or can you? Sure. Here's what you do. Subtract the top from the bottom, then square the bottom and the back, add the two together, and derive the square root to find your front. Or a squared plus b squared equals c squared. Let's try it. The bottom is 6, the top is 3, Subtract the top from the bottom to get 3. Now square that to get 9. Next, square your back. 12 squared is 144. Now, add the 2 to get 153. Now, get the square root of 153, which is 12.37 inches, which is how long your front piece will be. It's that simple. Now, let's talk a bit about the golden ratio for building our enclosures. These are considered the optimum dimensions to build your enclosures when there are no size restrictions. An enclosure built with this formula will have less panel vibration and unwanted resonances within it. To find the size of a particular enclosure, simply find the cube root of the volume you wish to use, and this will be side A. Then multiply side A by 0.7937 to get side B. Then multiply side A by 1.2599 to get side C. This simple procedure will make all of your enclosures sound better. Obviously, you won't be able to build all of your enclosures to this ratio, but always use common sense when building your enclosures. We will be using this ratio later in building our enclosures. So let's move on to figuring displacements. Whenever we determine the optimum size of an enclosure for any loudspeaker, the volume of the enclosure must have the displacement of ports, speakers, and braces figured into it. Earlier, we covered how to find the volume of shapes, which could represent that of your ports and braces. Now, let's determine how to figure the displacement of our loudspeakers in our enclosure. This formula isn't exact, but is within a tolerance of about 10% and has worked well for me over the years. The formula is as follows. Simply measure the distance from the back of your magnet to the edge of the basket and cube that. Next, multiply that by 1.2434 and you will get close to your displacement for that particular loudspeaker. Now, let's move on to part 3. Here we will begin by showing you how to derive teal small parameters from any loudspeaker you wish. Here is a look at some of the equipment you will need to do so. Here is an audio generator capable of generating tones from 20 Hz to 20,000 Hz. Next, we have an analog multimeter, which we will use to measure impedances. A digital meter fluctuates too much to get accurate readings. Therefore, we will use the analog. You will also need an enclosure of known volume to derive your VAS. Here is the loudspeaker in which we will be deriving the parameters, and you will also need a 1 to 2 K ohm resistor for your test. Before we begin, notice this dual voice coil loudspeaker. A dual voice coil is offered to give greater flexibility in its use, but for our test we will be hooking up the two sides in series. To derive your teal small parameters, you must have both voice coils in use. Hooking your voice coils up in series, you simply hook the negative side of one voice coil to the positive side of the other using a jumper wire as seen here. Then, you take the remaining positive and negative and wire that to your source. First, test the DC resistance of your loudspeaker with your multimeter before continuing. You may want to use a resistor to calibrate your meter. Now, in line with your positive wire, you are going to place your resistor. Since audio signal is AC, the placement of your resistor is not critical. Now, once you have hooked your resistor in, hook up your audio generator to your two leads. Now, hook up your meter to your speaker, making sure it is in the scale for measuring impedance. Next, turn on your audio generator and begin your test. The first measurement you took was that of DC resistance, and you logged that as 7 ohms. Now, we will look for our FS. To do this, simply rotate your audio generator in the lowest setting up and down the dial until you find peak impedance. Watch your multimeter until it peaks and begins to come back down. Then, read your audio generator and record your FS. The impedance at FS will be your Zmax. Now, find RO by dividing Zmax by RE. Our Zmax was 55 ohms. This occurred at 27 Hertz. Okay, we've come up with 7.857 for our RO. Next, find the square root of RO. Okay, 2.80. Now, find reduced impedance by multiplying the square root of RO by RE. Okay, 19.62 ohms. Now, find the frequencies above and below Fs that are equal to the reduced impedance, and they will be F1 and F2. Next, to find QMS, multiply Fs by the square root of RO and divide it by F1 minus F2. Now to find QES, divide QMS by RO minus 1. Next, to find QTS, we use QMS, which was 3.45, and QES, which is 0.50, in product over sum, QES times QMS, then divide it by QES plus QMS. Last, we need to find VAS. To get this, we need an enclosure of known volume. In this case, this enclosure is 1.4 cubic feet. Simply place your loudspeaker on top of the hole, ensuring a good seal. Next, measure the frequency response with the speaker in the enclosure, and this is FCT. Okay, that's about 56 hertz. Now, to find VAS, here's the formula. VB is the volume of the enclosure. And there you have it. Your FS is 29, your QTS is 0.43, and your VAS is 4.42. Now, with these parameters, box building is much easier. In fact, without these parameters, building a perfect enclosure would be virtually impossible. Now, let's get going on designing an acoustic suspension or sealed enclosure. Closed box loudspeakers are the simplest and most popular type of enclosure used in automotive applications. The low frequency response of a sealed box enclosure rolls off at a rate of generally 12 dB per octave below F3, which is determined by the driver's parameters and the enclosure size. Before we begin, it is important to note that the following information only applies to the piston range of the loudspeaker. We will start with an 8-inch loudspeaker with the following teal small parameters. It has a QTS of 0.23, an FS of 26.25, and a VAS of 2.78. Since size is no object, we will be building an enclosure with a QTC, or total system Q, of about 0.707. Loudspeakers for sealed enclosures would have QTS in the range of 0.35 to 0.60. The FS should be in the low 30 Hz range, and it should have a medium VAS. It is important that your cabinet be airtight as well as your speaker. Before we go any further, let me explain QTC. The QTC is the combination of the speaker and box interacting together. You will also hear it referred to as system Q. Now, a Q factor of less than 0.7 lacks bass due to overdamping, where enclosures over 1 will be boomy, up to about 1.5 where they become unbearable. It is important to note that lower bass cannot be obtained by making the enclosure larger after the QTC drops below 0.707. To find the optimum box volume using a desired QTC, use the following formula. If you already have a box volume of a known amount, then to find the QTC of the system, use this formula. To find the system resonance, or FC, use the following formula. And finally, to find your low frequency cutoff point, or F3, formulate the following. Now that we have covered the formulas, let's design a sealed enclosure. Referring back to our initial formula to determine a box, we want to get a volume with a QTC of about 0.707. Here's what we do. Take the VAS, or 2.78, and divide it by 0.707 over QTS squared minus 1. And we will come up with a box volume of 0.328. Now, we take our driver and determine the displacement is about 53.3 cubic inches of volume and add that to the box volume. This gives us a box volume of 620 cubic inches. Now, we can determine the optimum size of our enclosure by finding the cube root of the box volume and performing these steps that we talked about in the golden ratio section. The cube root of 620 cubic inches is 8.52. This is side A. Multiply that by 0.7937 to get 6.76. That'll be side B. And then multiply side A by 1.2599 and you'll get 10.73. That will be side C. Now, these are interior dimensions, so be sure to account for the thickness of your wood when building this enclosure. Now, here is our enclosure with a plexiglass view window. Now, let's talk a bit about damping. If you have an instance when your enclosure is undersized, it is possible to fill your enclosure with a fiberglass or polyester batting to offer an apparent volume increase of up to 15%. It may also help to control a system where the QTC is too high. Now, let's move on to our bass reflex speaker enclosure design. This is known as a tune-ported or a vented enclosure. This type of enclosure is considerably different than the sealed enclosure. Simply making the box larger or smaller to affect the optimum response is not possible. What we do with a ported enclosure is tune the port to interact with the tuning of the speaker in the enclosure. The variation from an optimally tuned speaker enclosure and port is known as ripple. A tune-ported enclosure has several advantages, one being higher efficiency due to the additional output of the port. The port, also known as a Helmholtz resonator, where the air mass inside the port vibrates in phase with the cone of the speaker at some frequencies and out of phase with other frequencies. The out of phase vibration of the vent coupled with the natural roll-off of the speaker increase the system's roll-off characteristics to 24 dB per octave. Now, in the way of ripple, the acceptable range in a bass reflex enclosure is between -2 and 2 dB. We are going to build our enclosure using a 10-inch loudspeaker with the following parameters: QTS of 0.26, VAS 4.80, and FS of 27 Hz. Optimum teal small parameters for a vented enclosure are QTS of between 0.25 and 0.45, medium to low VAS, and FS in the mid-30s and down. The following is a formula for zero ripple vented speaker enclosures. Now, let's plug in our numbers. 15 times 0.26 to the 2 to the 78th power times 4.80. This will give us a VB of 1.7. Our F3 is approximately 46. Now that we know this, let's find our port for our 10-inch enclosure. We will be using a port with a 6-inch area. So to determine the port and its length, you simply perform the following. To determine the radius of your port, you should take the radius of the speaker being used and divide by 2 and round up to the nearest whole number. For instance, the radius of a 10-inch speaker is 5 inches. Divide that by 2 to get 2.5 inches. Now, round up, and the minimum size for a 10-inch speaker should be 3 inches. Now, we have used a square port for this enclosure and have determined the length to be 2.2 inches. Now, let's calculate our perfect enclosure. Take VB, add the displacement of our speaker and port, and you will come up with approximately 3,047 cubic inches. Now, calculating your golden ratio, and you will come up with side A 14.5, side B 11.5, and side C 18.25. Here we have another enclosure. To formulate a vented enclosure when you don't have optimum dimensions, use the following formula. Now, let's move on to part 4 of our video. In this section, we will cover the designing and building of isobaric enclosures and bandpass enclosures. Presently, isobaric enclosures are one of the most popular compound cavity enclosures being used in car audio applications. With isobaric enclosures, not only can you get 2 drivers in just over half the airspace of a single speaker, isobaric enclosures also work to cancel large amounts of tone distortion that are evident in sealed box designs. Isobaric enclosures are fairly simple to design, and for the most part we have discussed the formulas that work for isobarics earlier in this video. We will treat this enclosure as if it were a sealed enclosure using the formula for sealed box design. We will enter the teal small parameters QTS and FS from the speaker and then divide our VAS by 2 and plug that into our formula. Now this calculation is for the rear enclosure, assuming that you will be enclosing the front driver. Now there are two ways to couple these speakers together. The first is to seal the two together facing one another and then mount one speaker into the enclosure, creating virtually one woofer requiring half the airspace of just one individual driver. The second way is to build the other speaker into a front cavity just large enough to house the speaker, keeping the magnet of the front speaker half the diameter size of the woofer from the edge of the rear speaker, as seen here. It is important to observe this spacing to ensure the near field of the rear speaker remain unobstructed. Ensure a good seal between cavities and apply the golden ratio whenever possible. Here is an isobaric enclosure ready for finishing, and it sounds great. Now, let's move on to our bandpass section. Bandpass enclosures are enclosures where the acoustic output is electroacoustically filtered by combining electrical and acoustic low-pass functions to produce a defined bandwidth response. According to Earl R. Geddes, the author of a well-written paper on bandpass enclosures titled An Introduction to Bandpass Loudspeaker Systems, to determine the bandpass order, simply sum the high-pass and low-pass orders. These enclosures are proven to have as trade-offs improved slope characteristics, lower high-pass cutoffs, and improved displacement power handling. For this video, we will be designing and building a non-symmetrical dual-cavity, dual-reflex enclosure using a 12-inch loudspeaker with the following teal small parameters: QTS of 0.51, a VAS of 3.90 cubic feet, and FS of 28 Hertz. Now, here's the schematic of a 6th order non-symmetrical bandpass system. Now, are you ready with your calculators? Here is the mathematical equation for the same enclosure. Apply the teal small parameters previously given. If this is a bit much math for you, we have calculated the formula for you and determined the enclosure size to be about 2 cubic feet. We will have a peak of about 4.5 dB and a cutoff at about 39 Hertz. Now, typically, when building a non-symmetrical enclosure, I will use a 2-to-1 ratio front enclosure to rear. So before determining the displacement of your rear enclosure, divide it in half to find your front cavity. Then proceed to figure the displacement for the rear enclosure, including the speaker and the port, and the front enclosure, just figuring for the port. Generally, I will tune my enclosures 1 octave to 1.5 octaves apart. An octave is the doubling or halving of a frequency. So if my rear enclosure is tuned at 35 Hertz, then I tune my front enclosure at between 70 and 87.5 Hertz. Remember, different drivers will react differently. Always apply these formulas when changing parameters. Here are some other tips to heed when building bandpass enclosures. Never carpet over your ports. Don't place your ports over your drivers or in the center of the box. A leak in your port or speaker enclosure will ruin its performance. Remember, laying a speaker on a horizontal plane allows gravity to take over and may change the cue of your driver. Do not obstruct your port by placing your enclosure too close to a wall or seat. Obviously, we are teaching speed in the install bays, so calculating each and every enclosure longhand is not practical. There are several computer-aided speaker designs for the PC, including one that we are currently working on. Also, included in your video, we offered several other formulas and a list of other reference material that we recommend for furthering your knowledge into enclosure designs. Now, let's review what we have learned. In Part 1, we covered acoustic theory, the dynamic loudspeaker, characteristics of the transducer, and we defined teal small parameters. In Part 2, we discussed basic geometry, the golden ratio, and displacement formulas. In Part 3, we talked about derivation of teal small parameters, calculating and building a sealed enclosure, and formulating and building tune-ported enclosures. Finally, in Part 4, we covered techniques in building isobaric enclosures and bandpass enclosures.
That about wraps it up for this video. Good luck applying your newfound skills, and remember, always have fun, keep an open mind, and make lots of money. I'm Mike Breault for the National Academy of Mobile Electronics. Goodbye for now. Be safe.
Hello, this is Mike Breault again. I'm here to tell you about the many training aids that NAME offers to you as a mobile electronics connoisseur. NAME currently has 3 sets of training videos. Our intermediate set consists of basic electronics, automotive electrical, tools and safety, and installation techniques. Our advanced series consists of electrical, auto sound, security, and cellular. And finally, our audio architect series. It includes woodworking, fiberglass, upholstery, motorization, enclosure design, which comes with this reference guide including several formulas, and rounding out the architect series is the Miracle Door Panel video. NAME also offers a SpeakerCAD software, which will assist you in building enclosures, putting the tedious task of calculations at your fingertips for the following things. It will derive teal small parameters, calculate optimum sealed enclosures, tune ported enclosures, calculate vent lengths, plot a graph of response, and help you design 6, 12, 18, and 24 dB per octave crossovers.
This software can be yours for only $79.95 if you have already purchased any of our videos from NAME. Finally, I would like to tell you about NAME's certification program. NAME will allow you to become a certified audio architect in the privacy of your own living room. It's simple. Just view all of the audio architect videos, answer 150 questions, and get 85% or better, and you will receive a plaque recognizing you as an audio architect from the National Academy of Mobile Electronics. Also, you'll receive this colorful t-shirt just for taking the test.
This concludes our video presentation. For suggestions for new videos or the release of other training videos, call NAME at 1-800-869-8448.